Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll discuss the final topic in the first chapter of 12th Mathematics, and that is binary operations. Now, we've already seen relations, and in relations, you have a set A and you have a set B. Quite often they're both the same set, that is A each, and you take one element from the set A, one element from the set B, and you create a set of ordered pairs of elements A, B. So you go from A and B to A cross B, right? So basically two one-dimensional sets becomes one two-dimensional set in a way, right? In functions, you go from one set to another set, right? So in this case, you go from two single sets to a set which has elements from both the sets. So from A and B to A cross B, here you go from A to B. What happens in binary operations is you have two elements from the same set A, and both of them combine, but they don't combine to give us an ordered pair of triplets. They combine to give us basically just another set of numbers C, right, which would be, let's say, this set. So if relations were to be represented as A and B become A cross B, and functions were to be represented as A goes to B, both these notations we've already used before, then binary operations would go from A cross A to A. That means you go from an ordered pair of numbers A, B to another number C. So in relations, you take two numbers and you make a set of ordered pairs. In functions, you make one number go to another number. In binary operations, that's why the word binary is used, you take two numbers, one from each set, A and B, and both of them go to a third number, right? If they went to, let's say, C, D, then it would be a relation, right? But it goes to C, that means it's a binary operation. There are some binary operations we already know, such as addition, multiplication, subtraction, and division. And the general rule for binary operations is, if a binary operation is represented by star, then generally what you would say is, the way you say for a function of two variables f of x, y, you would say star of A, B. But generally star of A, B is equivalent to A star B. This is just the notation we use. So whenever we write 2 plus 3, what we are actually writing is plus of 2, 3. That means the binary operation addition is one binary operation. So addition operation on 2 and 3. So plus 2, 3 is basically just a fancy way of writing 2 plus 3. And if you have generally binary operations that are not these fundamental operations, then you sometimes write it in this form. But these four fundamental operations we generally write in this form, right? So the standard definition, the general definition rather, would be a binary operation star on a set A. Again, a relation in a set A means you had two sets, two elements both from the set A. Binary operation on the set A means you have a function whose domain is both elements of the set A, like f of x, y. So it is a function. Just think of it as a two-dimensional function. Star of A, B, which is defined from A cross A to A. So A is a member of the set A, B is a member of the set A, and the binary operation is also a member of the set A. For example, if the set A is a set of real numbers, then you take two real numbers, you make a binary operation on them, addition, multiplication, subtraction, division, and the result is also a real number. That's why this is also the set A. This is also important. So it is a binary operation on a set A is a function psi of A and B going from A cross A to A, and we often write psi of A cross B as, like I already told you, A star B. Right. So plus can be written as a function going from R cross R to R, and that is given by A comma B goes to A plus B. Similarly, subtraction can be written as R cross R goes to R, and you have A comma B. Basically, this means minus of A comma B. Minus of A comma B is the same as A minus B. Right. For multiplication, again you go from R cross R to R. The reason we are writing R cross R to R is that there are two elements here, both from the set R, and you only have one element as the output, which is also an element of the set R. And you have A comma B is equal to AB or A multiplied by B. Right. Now, the thing with division is, okay, first let's just write R cross R to R, A comma B, which is A by B. Now, the first three are binary operations on R. That means on the set of real numbers. That means you add two real numbers, you'll get a real number. You multiply two real numbers, you'll get a real number. You subtract two real numbers, you'll get a real number. But division has a problem when B becomes 0. Right? Then A by B is not defined. So it will not be a function. If division is not a function on the set R, then it is also not a binary operation on the set R, because a binary operation first of all has to be a function. Right? But however, if we take a different set, R star, let's say, where R star is simply R minus the element 0. That means all real numbers except for the real number 0. If we take that to be the domain, then obviously the division of two such numbers will never be 0 either. So neither one of the three numbers is 0, and in that case this becomes a binary operation, because we've removed that point 0 where the division becomes infinite. So this is a binary operation on the modified set R star, where R star is the set of real numbers minus 0. Now, they can be defined on subsets of R as well. Right. So, for example, if you take addition, it is also a binary operation on N. Let me just remind you of what these are. R is the set of real numbers, Z is the set of all integers, N is the set of all natural numbers. Right. So it is a plus is a binary operation on N, because you go from N cross N to N. That means you add two natural numbers, you'll always get a natural number. But subtraction is not a binary operation on N. It is a binary operation on R, because it goes from R cross R to R. That is, the subtraction of N, or the difference of any two real numbers, is a real number. But going from N cross N to N would mean the difference of two natural numbers is always a natural number. But 2 minus 6 is not a natural number, because minus 4 is not a natural number. So they can be defined on a subset as well. But of course, you need to go from this set and this set into this set as well. So difference or subtraction is not a binary operation on natural numbers, because it goes from natural numbers, but it goes outside natural numbers. It goes to integers actually. Right. Now you could say N cross N goes to Z. That might be a binary operation, but binary operations by definition are defined from A cross A to A. So either R cross R to R, or Z cross Z to Z, or N cross N to N. Right. Now, if A is a finite set, all these were infinite sets, and what we'll discuss of finite sets now can be generalized for infinite sets. But let's assume A is, let's say, 3, 5, and 9. So now this is a finite set having only 3 elements. I'll just make it 4 just so that you're not confused with 3 elements and 3, 5, 9. So this is a set of 3 elements now, right? So A cross A is basically 9 elements. You can take 4 along with 4 or 5 or 9. You can take 5 along with 4 or 5 or 9, and you can take 9 with 4 or 5 or 9. So let's say we have a binary operation. We don't know what it is yet. We know that it's not addition, multiplication, subtraction, or division. We know that. Okay. So if it's a binary operation, then if the binary operation is defined from A cross A to A, then there are only 9 possible values of this. Right? You can only have either star of 4, 4 or star of 4, 5 or star of 4, 9 or 5, 4, 5, 5, 5, 9, 9, 4, 9, 5 and 9, 9. Right? If it's going from A to A, that means this can take 3 values, this can take 3 values, this total can take 9 values. Right? Now we are told that it's going to A. So all 9 of these will have a value either 4, 5 or 9. Right? So if I could give you the values right here, but it's generally easier for binary operators to draw a table. Right? So the number of entries in the table will be n, where n is the number of elements here. One extra will just be for the heading. And we can just fill up all these 9 entries within this table, and then we can say that this table completely determines the binary operation. So let's say you go row, comma, column. So this is the first. So 4, 5, 9, 4, 5, 9. Let's say 4, 4 is 5. Let's say all the equal ones are 5, just for the sake of it. So 4, 4 is 5, 5, 5 is 5, 9, 9 is 5. Yeah. Let's say these 3 are 4, and let's say these 3 are 9. Remember, we are defining the binary operation. This is not a binary operation that exists. I'm just trying to convince you of the fact that if you have n entries, n elements within the set A, then an n cross n, in this case a 3 cross 3 table with n square entries, completely determines that binary operation. That's what I'm trying to convince you of. So 4, 5 is 4, 4, 9 is 4, 5, 4 is 4. Remember, we are doing row, column. Right? These are 9 each. Now, these 9 entries could be anything. They had to be 4, 5 and 9, but between 4, 5 and 9 they could be anything. And every one of those combinations is a new binary operation star. Right? So basically what I'm trying to convince you of is, if A is a finite set having n elements, then n square entries in an n cross n matrix completely determines the binary operation. It goes both ways. Every binary operation will have associated with it a set of n square elements, right? Now, we are not talking about addition or subtraction. They are generally defined on sets which have an infinite number of elements, like in infinite natural numbers, right? But if it only has n elements and it goes from A cross A to A, then you can only have n square combinations, each one of them having a value equal to one of the n values, right? So you can have a total of n square entries, and every binary operation, let's just write BO for now, binary operation, it corresponds to one table, and every table corresponds to one binary operation. So I just made the table, and this is a binary operation. Right, now I don't have to write any binary operation in terms of multiplication or any other functions you know. I could just define a binary operation such that these are the final values. Here I have defined a binary operation. Right. Now let's look at some properties of binary operations which help us in categorizing them a little bit further. So the first is a binary operation star on the set X is called commutative if A star B, remember A star B is just another way of writing star of A comma B, is equal to B star A for all A and B belonging to X. Right? So this, you can easily see that addition and multiplication are commutative binary operations. Subtraction and division are not commutative, because A minus B is not equal to B minus A. However, A into B is equal to B into A, and A plus B is equal to B plus A. Right. The next operation, the next property, sorry, is that a binary operation star on the set X is called associative if A star B star C. Now notice this is always defined. A star B, if A goes from X cross X to X, sorry, if star goes from X cross X to X, that means A is a member of X and B is a member of X. But not only that, it goes from X. I'll just write A cross A to A because it will be confusing if I write X. So A is a member of this set, B is a member of this set, but not only that, the binary operation itself is a member of this set. So A star B is a member of X and C is a member of X, so obviously you can have a binary operation between them. And it's associative if this is equal to A star B star C. Now this is true again only for addition and multiplication. This is not true for subtraction and division. A minus B minus C is not the same as A minus B minus C, right? This becomes A minus B plus C, right? Now notice, only for associative binary operations does it make sense to write A star B star C without any brackets. You can write A into B into C, you can write 3 into 5 into 9, or 6 plus 7 plus 18, but you cannot write 6 minus 7 minus 18. In that way, you have to either tell us that it's 6 minus 7 minus 18 or 6 minus 7 minus 18. Of course, if you generally write it in this way, it's assumed that it's 6 minus 7 minus 18. So that's a convention we've adopted. Right. Also, 6 by 7 by 18 doesn't necessarily make any sense unless you look at it as 6 by 7 divided by 18. But this is not necessarily equal to 6 divided by 7 by 18. Right. So A star B star C is meaningless unless they are associative, unless we define some terminology in some unique way. And only addition and multiplication, out of the 4 general operations, only an addition and multiplication are associative or commutative. Subtraction and division are not. Also, there are 2 important things related to every binary operation. There is the identity and there is the inverse. So let's look at the identity first. By the way, identity, this is a word which is used again and again in mathematics, and generally it always means the same thing. It means there is no change. So the identity function is a function in which there is no change, y is equal to x. The identity element will be an element with which there is no change, as I'll define right now. We'll see a little bit later in a later video identity matrices, which will be a matrix which does not give any change. Right? So identity basically is sort of like 1. 1 for multiplication, 0 for addition. So let's look at the proper definition. Again, I'll not write the whole thing now. Given a binary operation star from A cross A to A, given this, an element E, it's generally denoted by E, belonging to A, if it exists doesn't exist always. So an element E, if it exists, is called the identity for the operation star if A star E is equal to E star A is equal to A for all A as members of A. Now what is E for addition? It is 0, because A plus 0 is equal to 0 plus A is equal to A. What is the identity for multiplication? It is 1, because A into 1 is equal to 1 into A is equal to A. And they are both defined on the same set R. So we see that the identity depends on the binary operation in question. Right? Subtraction and division are the same way. Subtraction has the identity 0 and division has the identity 1. Division, of course, as we already discussed, has to be defined on R star, because it is not a binary operation if defined on R. And finally, if you are given a binary operation star from A cross A to A, and you're also given it has an identity element E, then an element A which belongs to A is said to be invertible with respect to the operation star. Again, it has to be with respect to every operation. Operation changes, whether or not its invertible changes. If there exists an element B again belonging to A such that A star B is equal to B star A is equal to E, where E is the identity. Right. So for addition, if you have a number A, the inverse will be minus A, and multiplication, if you have the number A, the inverse will obviously be 1 by A. So this completes binary operations and the first chapter. In the next chapter, we'll start studying inverse trigonometric functions. Now I'll already just tell you a little bit about that. They will be the inverse of trigonometric functions. So the important things from these videos will be whether or not a function can be inverted, whether or not a function has an inverse. We've already seen that in one of the previous videos. Right, thank you.